And then we're going to go into working on your labs. The resistive force that opposes motion, that should tell you right off the bat what that is. Opposes motion or attempted motion of an object either past another object with which it is in contact or a fluid is called friction. Newton's second law states that the blank of an object is directly proportional to the net force acting on the object. The acceleration. Blank is the force directed towards a fixed point, the center of a circle, that causes circular motion. What force causes circular motion? Centripetal force. Is there anyone who should have missed either any of those three, really? Now, a lot of you did, but you shouldn't have, right? A law relating the intensity of an effect to the inverse square of the distance from the cause is called the inverse square law. I could see where you could get confused from that. Sorry, but I gave you 2 points for the last two. So I gave you extra 2 points for the last two questions, even though some of you got them. Huh? Well, I know, but that's why I gave 2 points on it to everybody. Some people got them right, but they still got the 2 point. The path of each planet around the sun is an ellipse with the sun at one focus is Planck's first law, and that was Kepler. Kepler's first law. Kepler's first, second, and third, right? You rewrite the question with the right answer, okay? And I'm going to go through why those are. Then you can start kicking yourself, hopefully. This unit and the next unit are kind of the most challenging units. So we're going into a tough one too. But, you know, that's not my fault. That's God's fault, right? He creates the laws on planets, not me. Then it gets a little easier, yeah. Energy, so we have momentum and energy, and momentum as vectors, and we have conservation of energy and all that. So, however, it builds off a lot of that what we've already learned. So, you may come out with hundreds on everything. I don't know. If the mass of the Earth somehow increased with no change in radius, your weight would what? Well, let's get this formula up here. So if you increase the mass of Earth, right, that would mean that this would go up. What's going to happen to your weight, which is this? It's also going to increase as well. The more massive object, the more the force of gravity that it's causing, the more bend in the space-time continuum, right? The more stretchy in the stretch stuff we played with. The Earth's gravitational field extends around any mass, whether you're inside and outside the Earth, and even though it gets very small as you get farther and farther away from Earth, theoretically, it goes through the entire universe, so B. So B is the best, okay? Let me see if I can find this thing. I just remembered it. Oops. Neil deGrasse Tyson gravity. Well, anyways, maybe later I'll show it to you. Anyways, it explains how something falls through Earth. If you start with a ball at the surface of Earth, and you could drill a hole down through the center of Earth, right? As you fall down through towards the center of Earth, what happens to your force of gravity on the ball as it falls down through that hole that we drilled through Earth? It gets smaller. And then once it gets to the center of Earth, well, all the mass around it is canceling out, so there's no gravity, right? Right at the center. It's there, it's just all canceled out in all directions. But as you fell, what were you doing? You were accelerating towards, in the down direction, towards the center. You're accelerating, you're picking up speed, right? You're picking up speed, going faster and faster, right? Where would the fastest speed be? Right at the center. Because through that whole time you're accelerating, even though your acceleration is doing what as you fall? It's getting smaller. Your acceleration is getting smaller because there's less of a force of gravity overall in that direction as you go down. Because some of it's pulling up. As you start to fall, some pulls up and you still have the downward, but your acceleration is still towards the center, but it gets smaller and smaller until it's zero at the center. But you're still accelerating in that direction, so your speed is still increasing. So you get your maximum speed right at the center, and then you start going this way, right? Then your force ends up again to be against the way that you're going. So you start going out to the other side of the Earth through the hole. And as it does that, that acceleration against it causes you to start to slow down. And it would match up until you get to the top, and then what would happen? You would get right to the outer edge, and then you'd start getting pulled back towards the center, so it would just bounce back and forth, wouldn't it? Okay. Except for the hot magma. All right, looking at this asteroid exerts a 360 Newton gravitational force on a spacecraft. Well, sometimes a little picture, I remember someone had a picture on theirs, helps. There's a spacecraft. The asteroid exerts a force. Which direction is it pulling it? This way, towards the asteroid. So now you can just answer it. The force is directed towards the asteroid, right? And if you've noticed on any multiple choice that I've given, I've never had a choice other than A or B. Number No. An asteroid exerts a 360 Newton gravitational force on a spacecraft. If the spacecraft moves to a point 3 times far away from the center, the force will be, okay, well, let's think of 3 times far. If you separate these 3 times far apart, right? My spaceship's getting worse. 3 times farther apart, what happens to the force? Bigger or smaller? Smaller. How many times smaller? Not just 3, right? 3 what? 3 squared. 3 squared. 9 times smaller. What's 360 divided by 9? 40. Well, we know it's not 0, so you just pick B. Because I never have had anything C, D, and E. That's actually not true. I'm just made that up. Because these are all A and B. All right. And then all we have is 5. Oops. A Weight Watcher who normally weighs 400 newtons stands on a very tall ladder so that she is 1 Earth radius above Earth's surface. This causes the FG here when you're separated this distance from the center. Okay? Now she builds a ladder to go out that distance plus an equal amount. What has happened to the distance between the objects? It's doubled. And if it's doubled the distance, how many times less is the force? 4 times less. And what's 400 divided by 4? B, right? So what should have been your grade on this page, Tommy? 10. Lorena? Honestly, what do you think you should have gotten? Probably. When you go over, like, 8 out of 10? Right. All right. It's always easier afterwards, though, of course, right? Train problem. Most of you did pretty well on this one. Oops. A toy train has a 7-kilogram engine. My drawing skills are lacking today. And 2 cars attached to it. The 2 cars are 4 kilograms each. And the engine is 7 kilograms. Right? Draw a sketch, that's there, and free body diagrams for the 2 cars and the engine. So on this car, we have the tension, we'll call it FT1. We have F perpendicular and FG. Now, like we have learned, the force on this one has FT1, right? Backwards, because the equal and opposite Newton's third law force of tension between these 2 cars. There's also this tension over here. We'll call that FT2. And we have F perpendicular, which would be the same size as these ones over here. For the engine, we have FT2 back, but we also have a force of the engine out, like that. That's moving the whole train forward. Its F perpendicular would be a little bit bigger because it's got more mass in FG. Okay, I took some combination of that. I've tried not to grade too hard on them, but do you see that? And then it says, what's the acceleration of the train? We also know that the tension between the last two cars is 50 newtons. So this is 50 newtons, and that's 50 newtons. They just go in equal and opposite directions. So if we take this sum of the forces for the last car in there, okay, the sum of the forces equals mass times acceleration. What are the forces? Just Ft1, because there's no loser in that one. What is Ft1? You were given it. 50 newtons. What's the mass? 4. Somebody put 7. So you just made they made a mistake, right? So those are the type of mistakes you can make on a test, right? If you accidentally put 774, just flipped it in your head, right? There you go. You screw up the whole problem. Minus 10 B. Off the start. Well, what would it be? 45 divided by 55. 82. B minus. I wouldn't take off all the points. 12.5. What's the other tension value in force of the engine forward? Okay, well, for the second one, we could sum the forces. And in this case, summing the forces is mass times acceleration. But we have a winner and a loser. Ft2 minus our Ft1 equals ma. It's Ft2 that we're looking for, but we know what Ft1 is. We found it already. No, we were given it. 50 newtons equals mass of 4 kilograms times A, 12.5 meters per second squared. So that gives us Ft2 minus 50 newtons equals 50 newtons. Lorena, what's 50 plus 50? It's 100, isn't it? She wrote down, I'm just making fun of you, to point out the fact of mistakes you can make on tests. 50 plus 50 equals 50. So stuff like, obviously she knows that 50 plus 50 is not 50, but it happens. Okay, now on this one, the engine, we have FE forward, the winner, minus the loser of FT2 equals M times A. And FE was, that's what we're looking for, minus FT2, which is 100 newtons. Now the mass is 7 kilograms, and A is 12.5. 7 times 12.5 is 87.5. Okay. Not bad, right? All right. Next question. The girl in the elevator. We should have all got this one. Okay. So she's standing on a bathroom scale in an elevator, and it reads 800 newtons. says to draw an FBD for the girl. Probably should have said, but anyways. What forces are acting on the girl? FG down. Which is bigger, FG or F perpendicular? F perpendicular is, right? Now, find the acceleration. We'll sum the forces. Again, what's the winner, what's the loser? F perpendicular minus FG equals M times A. What's F perpendicular? That's what the scale reads. So that's 800 newtons minus, what's FG? 60 times 10 or 600 newtons. What's M? What's A? Oh, you could solve for it. 200 divided by 60 is 3.3 meters per second squared. Right? Now, which direction is that? Up. It's positive in the upward direction because the net force is in the upward direction. For the A above, describe the two situations that could produce that. Well, you could be increasing your speed, going up, or what's the other one? Decreasing speed, going down. Both of those will produce an upward acceleration. At another particular moment, the scale reads 400 newtons. Draw the FBD, but this time FG is the same, but F perpendicular now is smaller. And we sum the forces, but we have a different winner. FG is now the winner, minus F perpendicular equals MA. And FG is 600 newtons minus 400 newtons equals still 60 kilograms times A. So what's the difference? It's still 3.3 meters per second squared, but what's the difference? It's down, right? And that could mean what? I didn't ask this question, but what could it mean? I hear a lot of voices. Courtney? Increasing speed going down or decreasing speed going up, right? Who has the outside accelerometer lab? You? And who else? And Wendy, yeah. So hopefully when you go to an elevator, you might be able to see it enough. This one doesn't work anymore, but the flick pack one they always have turned off. So you'll just have to go to City Hall real quick or something. So you could take it home with you. Do you have an elevator in your house? You? Anybody live in an apartment in the city? Sometimes, people live up on high floors. I've never really lived in an upward apartment. Well, I guess you got a basement or something. All right, I just asked a simple question. Okay. The box is being pulled up an incline, okay? The incline's at 20 degrees. Can't listen to that. A little hard, sorry. Well, I'm not sorry. Okay, what are the forces on this box? What other forces? Being pulled up 20 degrees. What other forces? F perpendicular. 90 degrees to the surface. What other forces? F parallel. The portion of FG. There's another one. What is it? It's against the direction of motion since it's being pulled up. FF. Right? Now, the acceleration of the box is based on the forces that are acting in the plane. What's the winner, or the upward force, since it's being pulled up? It's F pull. So that means you have one winner minus two losers, which are what? FF and F parallel. Those are both working against the pull, right? Equals M times A. Well, we know what the pull is. It's given, 200 newtons, minus F friction, which would be mu F perpendicular, minus, if you distribute the minus, F parallel, which would be FG sine theta, equals the mass, which is 30 kilograms, times A. Let's plug some more stuff in. What's our mu? What's F perpendicular? FG cosine theta, right? So now we got that. We plugged in 0.2. What's FG? 300 newtons. So we're going to have 0.2 times 300 newtons times the cosine of 20 degrees minus 300 newtons sine of 20 degrees equals 30 kilograms times A. What's 0.2 300 cos 20? $56.4. Minus 300 sine of 20. 104. 102.6. So we got 200 minus 56.4 minus 102.6. That gives 41 newtons. Equals 30 kilograms times A. So A will be 41 over 30. What's a newton over kilogram? Meter per second squared. Okay? That makes sense? You get all this, there's going to be a test on it. You know it already? Darn. What grade are you in? Oh, see. All right, next question. Tarzan, right? All right, so Tarzan's swinging on a long vine. Okay, like that. If you took this whole line, you could go around in a circle, and we're just going to have our radius 4 meters. Okay? Now, at the base of the swinging, right at the base, your your velocity is that way, but your force isn't that way. Okay, so your circle would look like this, but it's the velocity that's that way. The actual force that's causing that change in velocity is the centripetal force, which is a combination of Fg and Ft, the tension. And it's, whoops, it has to be directed up. So this one has to be bigger. Because it has to be directed where? The net force is also the what? Centripetal force, which is always directed towards the center. Oh, wait. Calculate the centripetal acceleration. Well, AC, you're given the speed, is 12 meters per second. And AC is v squared over r. Notice that it's squared. Many of you wrote down y, like tons of you really. You wrote down v squared, but then you didn't square it. Jeez, that really shook the whole building. What was it? Meters per second squared. And then I tell you down here, the sum of the forces is the centripetal force. Calculate the tension. And the sum of the forces is Ft minus Fg. Ft up, Fg down. Equals the mass times AC. And we want to find Ft. Fg would be 750 newtons. The mass is 75 kilograms. And AC is 36 meters per second squared. 2,700. $34.50. Okay. What the heck? That should have been the easiest. One more. Write your corrections on a separate sheet of paper. Right? By separate sheet of paper, I mean the back of a $20 bill. No, I'm just kidding. That's a Car Talk joke. Yeah, anyone listen to Car Talk? Send your puzzle solutions on the back of a, or whatever. Yeah, like the back of a half-eaten apple. All right, so this was FG is big G M1 times M2 over R squared. And we want to know the mass of this planet. Well, when you come, this works for anywhere, so mg would be the mass of the person, the weight of the person, okay, is Fg, which is mg. And then that would be big G times m, which is the mass of the person, times the mass of the planet, because you'll be looking at the force between the planet and the person. And the mass, it cancels out of the person, so now you can calculate what the mass of the planet is if we knew G. Oh, I got to do it differently. I didn't realize that. I'm sorry. I was just doing sort of, I got rid of, I don't want to cancel these out. I want to leave them in because I know what they are. Sorry. We're going to keep those in. What is mg of the astronaut? That's what she weighs. So that's 1,200 newtons. G is 6.67 times 10 to the minus 11 newtons times meters squared over kilograms squared times the mass of the person, which is what? So I decided not to cancel these. You see? Just so that's there. Because I used the whole FG because that's what I was given, 1,200. And I was also given the mass of the person, which was 80 kilograms. If you started with the other formula with G equals, you could have solved for G by FG equals mg. FG would be 1,200, m would be 80, and then you could just solve for G and use that. But since I started with that, the mass of the planet over the radius squared. Now most people got this wrong from this point, so they couldn't do the calculations on their calculator, right? Even though I continuously said, have your calculator out while we're doing the work, so you know how to use the thing. But no matter how many times I say it, I still only see like a couple people with it. .6 times 10 to the 24.